All right, so let's start. Good morning, guys. Um, um, so this is our agenda of today. Um, we'll, I'll first go Thursday assignment. Wouldn't take long, and we'll get into chapter two, and then in the end, um, at the break, we're gonna watch this video, and then in the end, we're gonna do a group activity on the abstraction. Okay. Um, so that's the plan today. So before we begin, I granted you guys accept the assignment. Okay. So go over your grades, and if you have gotten less than 100%, less than 10, take a look at the feedback given via the rubric. Okay, and then correct yourself. Okay, please. And then hopefully I can read the rest in module one by Wednesday. So that's my plan. Okay. So, so then basically going forward we'll try to grade like that. So basically we finish 1 week module and then so, next week we are finishing the grading of that week's module. Okay. So all right. But before we begin, any questions? Anyone? Any logistical issue? Anything? All right. So let's go ahead. Do we have one? So, Bridget, let's do the introduction during the. Oh, let's do it now. That's fine. This is Bridget, one of your. She was here last time, but we forgot to introduce. Go ahead, Bridget. So, Bridget was my 110A student in fall 2024, right? Yeah. So, the last fall. Yeah. And she applied to CCI during the winter break of that, right? That year. And then she got selected. So kind of, it's a proof that you all can apply and get that as well. Ask me how and I can do it. Okay. All right. So we're gonna talk about that in coming weeks. Probably, I mean, so Kevin also did that. Did the similar one, so not the same one. I might ask them to like show their posters to you guys in the break. Okay. All right. Okay, so let's begin. So we're gonna go over this one real quick. All right. All right. So I'm gonna do it over here. So click on this. So remove this one. Okay. Because we are not coding yet, right? So um, can you guys read this? Kind of hard, right? Because of the glare. Well, that's fine. So that spelling correct. Correct me if I'm incorrect with spelling, guys. Okay. Oh, so what's step one? Step one. By the way, it's a subjective question, right? So you may have a lot of opinions, right? Because there are a variety of ways making some of it, right? So mine would be different, but usually if it's straight out of ingredients. So collecting ingredients. Now, right. So that's one. There's always number them. Okay. So one, because we are formulating a recipe, right? So we follow a recipe from top to bottom. So we call it steps as well. In computer science, we call it the algorithm. Right? So in CS, those are synonyms. The recipe, the plan, the algorithm, all of those. Okay. So two. So it's my way. So I'm gonna go for my way from now on. So I'm gonna say. Remember, I actually graded this one. I saw 50-50. Number of you didn't put the subscript. Okay? Because in your assignment, you also need to do that. Right? You need to have stepwise refinement. So basically, you need to have subscript, right? So at least one, right? So this one is a good practice for that assignment. Okay. So two. So I would say prepare fruits. So mostly we need fruits, right? Or vegetables or both. So prep fruits. Again, this is my opinion. So an entire substep. So I'm gonna go inside. Now can see like 2.1. So always go for when you formulate the algorithm or the plan, always go for numbered bullets. Not just you know uh, sentences. Um, One cool reason is in computer science we have line numbers, right? Right. So you cannot read, right? Yeah, I know. Can you just turn off the light to see how you can? Is it good? Okay. All right. Yeah, but that's fine. Only for this one, we can keep it like that. Yeah. So then now this is 2.1. So it's just subset. So it's like, wash fruits, and again 2.2 cut fruits. And you may have other steps which are fine. Okay. So the next one, so it says three, put them in a blend, right? Into a blender. Okay. So you can write like blend, or add them to a blender. So I'm gonna write like this, add them to a blender. So so step four, I'm gonna add ice as well so that I can thicken the smoothie. Okay. So add ice, right? So number five, um, what else do we need to add? Milk. So smoothie usually require milk, right? So milk, add milk, right? Step six, blend. Did I? Okay, yeah, blend. And then step seven, so okay, all right. So it's simple but complete. Remember, right? So our algorithm should solve the problem. What's the problem? How to make a smoothie. So make sure it solves your problem. So that means this needs to be complete. So avoid any vagueness as well, right? So because if it is vague, then anyone, the person who are going to implement the algorithm now in trouble, right? Because the steps are vague. So it has to be, you have to make sure that the algorithm is complete and solves the problem. Okay, so make sure that. Right. So this that, and we can actually save this. So we're gonna click here to save. So you see that the link over here going to change, right? So that's that. Now we're gonna go back and then reply and then do the rest. Right? So this is another practice for you guys. Um, right. So I'm gonna copy paste code first, just the steps, right? Um, right over here, and then select all again. Change the this to pre-formatted. Okay. So in the end, now in HTML form, we're gonna actually do this. Okay. So to add the rest. So, so right here, so I'm gonna copy paste this. So that's the template for embedding, right? And I'm gonna replace this part with that link. Okay. I saw some of you guys, like very few, um, did this one in the text mode. You have to do this in HTML mode, right? This is part of HTML code actually, right? So embedding. So you have to do it in HTML mode. Okay. And also, there was one actually missing the items. So if you miss that, then it's gonna be really narrow view. Okay. So make sure that you can always toggle back and forth and verify and just reply. Okay. So that's that. Okay. And you can see that right? It's kind of appearing like code, and also it's structured for, um, like nicely, right? So, uh, all right. Any question? So, just remember that in big systems, we are getting into something like little bit big, right? Coding, right? So, this, they are filling up that foundation towards that. Okay. So, we may feel like these are very simple stuff. Everything starts from simple, right? So, that's what we are doing to build that foundation. Okay. All right. So that's that. And then we're gonna go back and then we're gonna start the side book and then do the rest. Chapter two. Okay. All right. All right. So could you get the lights? I think we can. We are good now. Thanks. All right. I'm gonna quickly go over this stuff, but um, hoping that these are also again conceptual topics, so we can actually focus more attention to more technical sections. So these are the components, um, like common components of computer. We have a CPU and memory, keyboard, and basically CPU and memory kind of allows us to our brain, right? Our brain has memory, and we also do cognitive things, right? Tasks. So CPU executes the code we give, and also access memory. So keep this two together, kind of a like a brain. CPU has two units. So one is arithmetic and logic units, ALU. Okay. Um, and then it has controlling basically um, it controls this stuff, right? And also dealing with the memory and also the inputs. Okay. All right. All right. So memory is called random access memory. So it's a short form RAM. Okay. So that's the hardware that stores memory. And then actually we call it the volatile memory because once we turn off the computer, it goes away. Okay. So non-volatile memory is something that we have They are non-volatile because they stay inside um, once you turn off the computer. Right? All right. So so keyboard is an example of input device. What are other input devices? Yes, keyboard. Okay, so controls. What kind of controllers? Joysticks. Okay, joysticks. Yeah, that's one. Anyone else? Yes. Mouse is a good example of an input device. Touch screen, the touch. Anyone? Game controller. Yep. Okay. Um, there are more examples. Microphone is one. Right? Yes, motion controls. There's one more obvious one. Camera, so video input, right? So if you also want, you can also think of internet also as an input device. So it's both an input and output device. Okay? All right. So the screen is a example output device. It can be speaker, right? There are other types of output devices as well. But these are common ones, like typical computer has a keyboard for input and screen for the output. Okay. All right. So this one is an important topic. So clock speed. Okay. So, so you may have seen this when like you try to buy a computer or a laptop. You see this anything like the speed, the CPU speed is like 1 gigahertz, two, three, something like that, right? So basically, so gigahertz means 1 billion cycles. So basically, it's saying that it takes um, right. It processes that many amount of information um, in a second, right? So that's that. So in other words, basically, sometimes we call one single piece of instruction is a um, single instruction or simple instruction. So CPU usually take process that set of instructions, say for one instruction in a single CPU cycle. Okay. So that means in 1 billion of a second, actually complete processing one instruction. Okay. Like for example, um, 1 plus 1 is a 1 instruction. Okay. This is also kind of, we call it a simple instruction as well. That means this whole thing, if you take one cycle and then just this. Okay. So there are some instructions that may need more than one cycle. So we don't actually call them like simple instructions. We're gonna get into those later in the class. So, so basically, um, usually a CPU takes um, process um, simple instruction like this in a single CPU. Okay. So this is now we can actually formulate something that is important, right? So let's say, um, so let's say um, write this table, number of instructions. So number of cycles. CPU cycle. Let's say one CPU cycle, um, let's say one instruction. Let's say like this step in one instruction. Let's say two instructions. Sorry, takes just to go the other way. So yeah, one, three, four cycles. Let's say one and two. All right. Let's say two. Four. So three instructions. Take six. And you can see that, right? That there's a relationship between the two, right? We call it like a linear relationship, it's proportional. So if we go like n over here, it's gonna be 2n, right? Right? So there's like a single instruction requiring two CPU cycles to process. So let's assume like they are all kind of same, like very similar types. So we have two, then four like that. And you can see that over here, so this is time, right? Right? So, for example, if I would say if one cycle is nanosecond, right? So let's take the time over here. So this is 2 nanoseconds, 4 nanoseconds, so 6 nanoseconds, right? So likewise, 2 nanoseconds, right? And you can see that the time is proportional to n, right? N over here, so we have 2n. So 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 this is proportional to this, right? So in certain situations, this number of instruction is actually proportional to the size of the data input that we want to process. So understanding this relationship is important in future classes. So the more we have the data, the more time we take to process it. Okay? So there's this kind of a relationship, and you will need to like it's beneficial to understand this relationship because again, single CPU cycle has a constant amount of time it needs to. So, so that means to process more data, we need more time. And that's the revelation. Okay. So, but we don't need it now, right? So it's good to understand that in particular future classes. Okay. All right, so let's go to all right, so let's do answer number 4, guys. So assume you made today the clock speed 3 gigahertz will generally execute. Yeah. And why is that? And then there are other things got into like architecture, right? And then the memory, other things also factor in, right? So that's why. All right. All right. So we went over that. Okay. So computer, inside the computer, we have switches. So those switches, there are two states, right? 0 and 1. So 0 is the off state, 1 is the on state. But what's the physical interpretation Yeah. So what value? What is the value? Yeah. The okay. So sorry. No, no. I understand. But um, well, I'm asking physically what we are representing in that 0 and 1, right? Or not? No? Yeah. So that's actually the voltage. Okay. So the physical element we use is actually the voltage. So basically, these are transistors, right? So those are the switches. So, um, like for example, let's say this is the voltage, and let's say this is time. So let's say pi is on, 5 volt, so around this much usually, right? So this is one, the on state. So there's a threshold. If we go below that, then let's say two, and we say that's actually zero. So let's say it went down this far, it is zero. So that's actually electrical signal fluctuating between two voltages, usually pi and zero, but there's a threshold below, let's say two, it's zero. Okay. So that's why computer use current to operate, right? So that's happening in the transistor level, so physically. Okay. Yeah. So that's the two states, right? The on state, the off state, and then bunch of these gives you bytes and all those things, right? Okay. So um, so representing inside the computer, so representing this numbers, it's usually straightforward, and later on you can actually convert between number systems in the class. But how do we do it for the other characters, like for example this percentage or dollar symbol, right? So um, there's no like for digits, for numbers, it's very straightforward, right? But for characters like this, there's no straightforward way to tell it because computer only understand those numbers, right? So then you have to come up with a protocol that everyone agrees into like consensus. We can need to come into a consensus among, let's say, computer scientists in the world and say that okay, so let's create a standard, and then this should be that. And first such that standard came in, I think, the 60s, which is the ASCII code encoding system. So basically, there's a binary or bit code, and then the respect to decimal value and the character we represent, right? So the characters beyond that, actually they are non-printable characters. So 0 to 32, they are non-printable characters. These are all of these are printable characters. So we say basically 33, and with this bit code represent exclamation point mark, right? So now this is a photo code sample. So everyone agrees to this. Now we can convert between, and we can represent these symbols in the computer too, right? So, but there's a problem with this. What's the problem with ASCII? It's small. Too small, right? So, do we only have this set of symbols? No, right? We have other languages, other scripts, other symbols, right? Like, like for example, square brackets, right? Or other language script as well, right? So that means the depth of this is 128. So we need more. So so came Unicode, right? So that has it started off with 8-bit Unicode, then we used that, and then we went to 16-bit Unicode, and then now we have actually up to 32-bit Unicode. Okay. So nowadays we even have code point, Unicode code points, even for hieroglyphs as well. Okay. So you can actually represent those like Mayan languages even. Okay. All right. So um, yeah. So that's that. So let's go to this one. Okay. But before that, I'm gonna let's work out a small workout, guys. You guys going to help me, okay? So all right. So I'm gonna write um the number of bits this side, number of states. All right. I have one bit. How many states do I have? Two. What are the states? What are the states? Zero and one, right? So there are two states. So I'm gonna say like 0 and 12. Okay. So basically it's two, right? All right. So let's write for two number of bits. What are the states? How many states do we have? Four, right? What are the four? Help me. Zero, 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 one, one, zero, one, one. Right? Right? So I have two bits, and the other combination that I can have possible. No more than that. Right? And there are four. Right? So these are the two bits. There is one, there is one. So those are the two bits. So one can have zero, other one also can have zero. The first one can have zero, other one like that. So these are all four states. So number is four. Okay? Four states. So I'm gonna go to three now. What are the states? How many states? You can now guess or calculate. Let's try, right, shall we? All right. Zero, zero, all zeros. That's one. Let's start with that, right? Then zero, zero, one. So you can write this first with the zero in front, right? So zero, one, zero, zero, one, one. Okay, if you cover this one, that's actually this, right? All right, so we covered that. So now we used up that, so now we're gonna basically next one, one, zero, zero, one, one, zero, one. Next one, zero, right? One. Do we have more? That's it, right? There's no more. So how many? There like nine? Eight, right? This is eight. All right, now do we see a pattern here? What is it? Doubling every time, right? So this is two to the one or one. 2 to the 2, 2 to the 3. Then what's the next one? The 4, 16, right? Yeah, 16. So 16 is going to be 2 to the 4. And then the next one is going to be 32, which is 2 to the 5. So in other words, basically, if we only have one bit, we can only store two pieces of information. Have 0 and 1. Okay? If we only have two bits, uh, binary number, we can use it to store four pieces of information. One is 0, 0, one is 0, 1, 1, 0, 1. And you can see that with that number, it goes up, right? So if we have 32 bits, right? How many states do we have? If we have 32 bits, so this is 4 and 5, right? So, right? So if we have 32 over here, 2 to the 32, right? So if we have 32-bit number of bits, we can use it that depth to represent 2 to the 32 amount of information. And you can see that with that numbers go up really rapidly, right? So it's really important to understand this. And I realized that the depth of the bit, the more the depth of the bit, the longer the bit, the more the amount of information that you can actually store inside a computer. And that's why I remember, early computers, like 5, 10 years ago, it was 32-bit computers. You remember, right? So nowadays we moved to 64-bit, right? Right? So one reason was that 32-bit computers couldn't handle more than 4 gigabytes of memory because we used up all the combinations, right? So that's the highest amount it could handle. So we needed to have more memory, so we had to nowadays we use 64-bit computers. So it has a lot of memory depth that it can handle. So you understand why now, right? So so it's actually so with 64-bit actually we have a way longer, a larger that we can support right now amount of memory. Okay. All right. So any question on that one? So it's not that math heavy, like just being able to recognize this pattern is really important. Okay. So it's the relationship between number of bits and the amount of space, the number of space it represents. Okay. So if we have 32-bit number, 32 bits, this many combinations of that exist. So this many pieces of information we can actually use, store it using that. Okay. All right. All right. So let's start this one. So before we getting into this one, okay, so I'm going to every time I do that, it's also a good kind of a way to understand that as well. So this is binary. So we're going to get into that in a moment, guys, okay? But let's write, so I'm going to write this number, okay? So let's say I'm going to change the number. Yeah, let's put it 234. Okay? So this is base 10. So regular number with everyday use. I usually don't write this for regular numbers, right? So this is base 10. So I'm going to break this number into three parts. Let's say like um, I would say um, there are trillions of combinations. So I can think of one. Okay, let's say 90. Okay. Um, well, I'm gonna go 120 or something. 120, and let's say 80. What's the rest? 34, right? 234. So the sum. Okay. But I only pick three. We will see soon why I pick three. Right? You pick three numbers, and then if you think of combination of those three numbers that sums up to this one. So that's the strategy. So think of how many such combinations. You can actually there are probably math on that, but probably millions if not trillions. Okay? Combinations. I can write one over here, and the rest over here. You can write 10 over here, and then it goes on. But there's a one interesting combination that really fascinating in number theory. Forget about number theory. There's a one combination of three numbers that is really fascinating. What is that? That's my question. Rely only on subs, okay? No subtraction. Okay. 430 and 200. So 200 here, 30 here, and the rest over here. Um, so 200 here, what's the biggest one? 30. And what's the other one? 4. Um, that's also, yeah, combination. All right, so let's stick with this one. So someone saying 200 here, 30 here, 4 here, right? Why is why is fascinating? Yeah, it is fascinating. That combination is the one that I was actually. Yeah, you're right. I think I think I understand what you are trying to say as well. So basically, it tells you um, the the parts of the number, right? So the places, ones place, tenth place, hundredth place, right? So let's break it down. So this is not good. So the fascination combination is 200 plus 30 plus 4, right? So to reveal even further, I'm gonna write it like this way, right, guys? Okay, so 2 times 100 plus 3 times 10 plus 1 times 4, right? And then let's go even more relations, right? 2 times 10 to the 2 plus 3 times 10 to the 1, 1 times 10 to the 0, because 4 is 1, right? So, oh, let me, very, um, should have written it this way, right? 4 times 1. Okay. So this is this, and this is this. And you can see, so here's why, right? Oh, sorry, yeah, 4 times, right? So here's why, right? So we call this the 100th position, 10th position, 1 position. And that's what we learn, right, in the school, right? So when we kind of like break down the digits of a decimal number, the ones position, 10 position, 100 position. Here, here the facts actually. This is why. So basically, we say 2 is the most significant digit because it had 200, and 4 is the least significant digit because it just have only 4, right? So those are also some naming there as well. So you can see that any number, you can go to this beyond the decimal point. We don't need to, right? So 10 to the negative 1 beyond, like for example, this one, 10 to the negative 1, right? So you can go increase up to positive infinity this way. You can go up to like 10 to the negative infinity that way. So basically, it can break down any number we have, right? So and you can see that there's one more like more patterns over here, right? What else can we see over here? This is a decimal number, and these are the three decimal digits we have. So these are the digits. The three, four are the digits. So it's decimal. So base 10. So you see 10 over here, right? See that? So this is base 10. You have 10 over here, right? So that's one pattern, one another pattern. So if it is base 2, then what should we have over here? 2, right? And that's what we have given here. All right. So you can see that. So this is the corresponding decimal value. So forget about the middle line, but we exactly have what we have with the base 10 here instead of base 2, right? But the same idea, right? So basically, so rather than even throwing this in front of you that way, this the better way to actually get into that one, right? So any number have this form, and then that's the I would call this the anatomy of a number. Actually. Okay, so and we can actually transform the same pattern to that one. So let's play with some of these. So if you add just one, this is one also in decimal. If you add one more here, this is one in binary, so it's actually decimal value is 3. So how does it form? 2 to the 1 plus 2 to the 0. This is 2 plus 1. This is 3. Right. So that also gives you a way to color back and forth between decimal and binary. Understand, right? So, and then this is the decimal number system, how it works, and you can transform the same pattern in understanding the binary system. Okay? All right. So let's use some of these. Let's say, what is 7 in 4-bit binary number? So 7 in 4-bit binary number. So this is 7, but still this is 3-bit, right? So if you consider this 0 bit over here, this 0111, right? So let's say 0111, right? Right? Okay. All right. Any question on this one? All right, guys. It's half May, so let's take our 5 minutes break. Okay? So, and after that, we're gonna watch the video on Bloom's action. It's just table. Okay, just okay, yeah. So I will go there. Okay. So you understand the number of states, right? So we have 1 bit, then we can have 2 possibilities, right? So that you have four, right? One six, second, third, fourth. So if you have three, we have eight here, and we're gonna have 16 over here for we're gonna divide all of this. So you can see the number of is 2, 4, and 8, and then these are all. The pattern is that we double each one. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and yeah. So that's the pattern is the power. So you can write the same pattern in powers, 2, 1, 2, 2, 2. Now, this one and this one has a similarity, right? So number of bits 2 would be 2. Number of bits 3 would be 3. That's the pattern. The number of bits 32, we have to do the 32. Many bits, right? No, it doesn't matter. That's a good question. Yeah, it doesn't matter. But for the simplicity, you can start off with from left to right. Yeah, left to right. You can do it. Yes. Yep. Oh, it doesn't work? Oh. Oh, okay. Yeah. So then you are logged in your Canvas account, right? All right. This is that's it. Okay. Yeah, make sure this is your Canvas account. Okay? Otherwise, someone else will buy it. Yes. Oh, yeah. This should be clear to the point. So if you guys, Simon is prompting you to select the section, guys, then it should be 005 for this class, okay? Yes. The section? It comes to. You may have done it already, but don't worry too much because if you have picked the wrong one, I can always change it. I can check it as well. So it's not a big deal. Just for mine, I see everyone together, but I wanted to see the two classes separately. That's the point. So it's not going to affect you. So don't worry too much. Okay, okay. It's just you're fine. Oh, we have clubs. Yeah. Bridget, we have a robotic clubs over here, right? Yeah. I know there's a robotic, specific robotics club, but very long ago. Definitely, engineering should have one. Yeah. So courses, I'm sorry, I don't know whether there are courses for the robotic courses. CS don't have, right? Yeah. What's your major? Okay. Okay. So, Um, yeah, might want to check engineering departments. Yeah. But there are firms. Yeah. They meet like twice a month, once a month, kind of things. Yeah. And we also have some clubs over here. Um, oh, okay. Okay. Alright. So, but this is a good first class that you can take, yeah, because this teaches the fundamentals of which you require in into, right? Yeah. Yeah. Oh, okay. Um, yeah, I mean, if you want, I can help you design as well. Yeah. Um, okay. Join the Zoom office hour on Friday, and I can talk in length. Yeah. So there's two people. By the way, guys, remember we have office hours Zoom. Last week one was 3 to 4 actually. This week also I might change the timing, but two people joined and then had a discussion with me. So feel free to, okay, and if you can't, and then you can demand a separate time for me as well, and we can decide through emails good time. Okay. You got me now. You guys can, you know, you know, if you can actually get, reimburse this money that you spend for books and stuff from government sometimes, depending on the other things too. So consult financial aid office, ask how, and they are there for you guys. I mean, get help on how to get financial aid. And that's not just for books, other things as well, like like commuting here and uh, all sorts of stuff, for stuff. Financial aid office. You can actually like call or online set up a one-on-one meeting with them with them, and they are the experts. So they know how to help us to get financial aid money from government, state government, college, right? All right, guys. So let's go over this. Um, so for this video, actually from University of North Carolina. So they have a like online learning center. So they put nice videos actually. So here's the one that so I'm just gonna publish it. Oh, sorry. Uh, I already published it. Yeah, this one. Okay. Already published. I mean, shouldn't have, but that's fine. All right. So we're gonna watch this video. So this basically it uses. So basically, the it explains the core idea of taking college classes. You learn something and then you use that knowledge to create something new. Here in computer science, basically you learn how to code and then basically use that knowledge to solve a new problem in code. That's the goal, end goal, in particular the CS. Okay. So, but it's not that directly linked, right? So there are certain ways, steps that you have to go through it, and then this video actually shows you that. Okay, it in a kind of metaphorical. You will see what the metaphor they are using. Okay, could you get the light? Thanks.
According to Bloom's revised taxonomy of cognition, there are several levels of thinking, ranging from the simplest forms, such as remembering and understanding, to the highest levels of thinking, such as creating something new from what you have learned. Professors ultimately want you to get to the highest levels of thinking, but notice, the highest levels of thinking rest on the foundation of the lowest forms of cognition. In other words, your ability to think critically will depend in part on what you remember and understand. So, the first step in becoming a great thinker is to spend time memorizing and understanding information. The more you know and understand, the better your critical thinking skills may become. After memorizing and understanding information, you also need to practice engaging in higher forms of thinking. How do you do this? A particularly effective way is to anticipate and create the questions you think your professor may ask on exams, taking care to make sure your questions reflect the different levels of Bloom's revised taxonomy. For example, remembering questions are those that involve recognizing or recalling facts, such as, in general, what do vampires look like? Or, what time of the month do men turn into werewolves? Understanding questions are those which involve explaining or describing concepts, such as, describe the steps involved with changing from a human into a vampire, or, why is a vampire a threat to society? Applying questions are those which involve taking what you have learned and connecting it with real-world examples, such as, knowing what you know about vampires, which one of your friends is most likely to be one? Or, considering your own health, are you a vampire? Analyzing questions are those which involve examining the components of a concept, especially to compare the concept with another concept. For example, compare and contrast vampires and werewolves. Evaluating questions are those that make some sort of a judgment supported by evidence, such as, which is better, a vampire or werewolf, and why? Which, a vampire or werewolf, would be most likely to win the Ninja Warrior competition, and why? Creating questions are those that involve taking what you know and generating something new with it, such as, what type of creature would you have to be in order to fight both a vampire and a werewolf? If you were allowed only one tool, what tool would you create to defend yourself from both vampires and werewolves? Generating critical thinking questions can be a challenge, but with practice, you can effectively anticipate your professor's exam questions. If you have trouble, visit the Learning Center.
All right. So find the answer and I can answer right now, guys. Okay. All right. So could you get the light? Oh, thank you. All right. So let's continue our lesson, guys. So um, this characters and numbers, the information that we actually store in the memory, in the end, they have this kind of form, right? So they all comes down to zeros and ones. Okay. And this actually shows you that this animation. So basically, so basically, you're saying C12. So we need S, right? And then E, right? Right? A and T. So that's seat, right? All right. And a space, right? Sorry, colon and space, and then 12. 12 is this. Okay. This is 12 in binary form, right? Okay. So you can see that the way it's stored, right? What kind of way is actually? So memory is arranged. Yes. Okay. Another name, top to bottom, sequential, right? So memory is arranged sequential. So that one after the other. So this one memory cell, the next memory cell, like what? All right. So it's basically just this value was arranged sequentially, right? But when I memory, yes. So it's the same, right? So actually, it's an encoding system that uses binary numbers. So you can see that if you count, there are 7 digits over here, right? So that's the length of the ASCII system, right? So this particular combination represents biggest, right? So to represent this big S, you need this encoded number inside the computer, inside the memory, right? So that's what it is. Um, the base 10 value? Yeah, so we don't usually need that, right? So it's in the encoding system. So if you go to the previous sector right here, right? So like bit is, right? So it's this one, right? So it's actually 83. So it's just to show you that, but we don't. I mean, computer doesn't show 83 something anywhere. It just shows this one. So this is only to show you. Okay, this is uh, the actual converted decimal number between the so in the SQ2 encoding system, SQ encoding system. Did I answer the question? Oh, just 83. So that's a really good question. Yeah. So 83. So basically, you can over here. So we use 12, right? So over here we had 12, right? So right here we had 12, right? So that 12 is this. Not an ASCII number, right? So we use ASCII only for symbolic values. So that includes text. Yes, we have 0 to 9 also in the ASCII system, right? So we also have 0 to 9 in ASCII system too. But these are this in text form, right? So imagine we are writing an email and we have letter 9 there, right? So that's that, right? So we need this form to represent this 9 in text. But in numbers that we actually work like multiply and so on, we can directly convert it to binary using kind of the way we saw earlier, right? We're gonna get into that actually in Thursday, how to convert back and forth from decimal to binary, right? Don't be confused. This is in text form. So if you want to do text form 83, then you basically first put this 8 and then put 3. So this one. So you need 2 in text form, right? So yeah, so basically here this part is that's a good thinking actually, right? This part is in this one, this part is um, pretty much represented as fixed, and this one represented the whole number as whole number in binary. Okay. Yeah. So probably I mean, it's good to, I see your point, right? So in here, it's just as a whole number in binary. You see that, right? So it would have been better if the site would explain what they intended to for you to say, right? So in this case, yeah, this part is fixed up to the space, it's fixed, and then it's the number. So yeah, right. But that's a really good catch or good question. Did you guys get what she is asking, right? So over here, up to the space, it's actually ASCII, and then we have this 12 number as a piece. That's why it's 001100. Think about it this way, right? It only wanted you to realize how the memory is arranged and stored. That's all. Okay. So it wanted to show you, okay, how text memory is arranged and then how a number is arranged. All right. So, so I'm gonna skip this one. Is like yeah, this straightforward. So the same way we have the metric system, we have a similar kind of system in number of bits, right? So and then that's the only difference is like kilo we have 1,000 over here, right? But here it's 1024 because these are 2 to the power, right? So 2 to the power 10 is 1024. So it's actually kilobits, okay? But it's not exactly 1,000, right? So that is very important to understand. Same for when you go to like giga, right? For mega, we have 1 million, so it's 10 to the 6. But this is the exact number because it's 2 to the power 20, little more than the 1 million. Okay. Likewise. All right. All right. So the RAM, so the random access memory is actually it's called data temporally, right? So we call this volatile memory, right? Because why we call it volatile memory? The RAM. Yes. Yeah. So when we turn off the PC or computer, that disappears, right? So it's volatile. But the thing that we store in the drive, the hard drive, the CG or the jump drive, anything, they stays even though we connect, right? Disconnect or turn off the computer, right? We call them non-volatile memory. Okay. So the RAM, regular RAM, is actually temporarily hold while basically the computer is on. Okay. All right. Um, let's go to. All right. So let's play this animation. This actually shows you um, why why having large memory benefits. Okay, so so first one is the CPU. You can see that this size of the square represent the 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 same, right? So that means it's the same CPU. You can see the only the difference in memory, same hard drive, right? So so the first one, first CPU, first machine, right? So takes only pieces of chunks and then process it, right? So with programs, so you read chunks and then process, right? So you can see that you can basically access smaller chunks and process them. But if memory is large, right, you can actually process larger chunks. So number of memory reads are smaller compared to, right? So the more memory reads you have, the more slower you are running, right? So that's why you having large amount of memory helps. Okay. So that one runs fast. All right. So cache. So we talk about CPU. There's a dedicated memory um, for inside the CPU. We call it actually cache. Around like cache. Okay. Like cache. So you have seen this, right? So when you buy a computer, what do you call it? Level one cache, level two thing, right? So that also like if you have higher numbers, the better, right? So the reason is this, right? So if you have a cache memory and it's actually sitting inside the CPU, right? So that is really that inside means really easily accessed and fast as well, right? But the thing is, CPU is not that large, right? It's a small chip, right? So that means the amount you can put in is actually smaller. So that's why this or this level one to three cache is like 512 megabytes, smaller compared to gigabyte range memory. Okay? So one other reason is the way the cache works is actually usually operating system handles it. The way it's actually used. So usually it's like this. So let's say you have a program, but um, you frequently use one piece of memory regularly. So the operating system recognizes that and then it decides, okay, this if I put it in memory, I have more memory reach for this single piece. Why not put it in the cache so that if you can access it really quickly, right? Because rather than having a lot of memory, direct memory reads to read a single piece of data, why not store it close by so that you easily access it, right? So that's the idea. So always decide that and put pieces of memory that you usually frequently use in the cache. Okay. So and then sometimes we call the physical device and it's called registers. That's another name of the cache. Okay. So that's what the usage of cache. Again, if you have more, it's more the better, but there's a limitation. Okay. All right. All right. And cache is faster, way faster than memory. So it's also that basically the fastest memory. And next is regular memory and drive terabyte. So speed increases, storage increases. All right. I think we can move on to. So we're gonna get into this one later, guys. I think we can skip this one. Most love already talked about it. Talked about it. Um, it's this pattern, okay, that keep on happening. Um, but if you take a log scale of it, the number of transistors per IC per chip is mostly aligned, and it continue. This trend is continue over the years, and then probably in the near future also it's going to continue. I'm not sure when the quantum computing comes, it may probably have a leap. Right. All right. All right. So let's go to so again, just you can read and answer, guys. So we're gonna go to this one, binary numbers. We're gonna come back to this. Not come back. Sorry, we're gonna start this one Thursday, guys. Okay. So this require a little good attention. So we're gonna dedicate kind of entire Thursday into this topic, conversion between numbers. So please do not skip Thursday class, guys. Okay. So it's an important lesson. So we're gonna go to this one. I think it's the so these two, 2.8 and 2.9. We're gonna jump to abstraction because this topic is required for our today's group work. Okay? It would take probably 15 minutes, or we have good amount of time to discuss. Okay? And hey, let's play this. We talk about abstraction, right? So, so this is talking about abstraction of data. So here is the data over here. The purple high is data. Okay. All right. So let's play this animation. So you can see that lowest level of abstraction. And you can see that, right? This is a lot of information, right? But you also don't understand it as it looks, right? So it's the lowest level. So it's all in binary. So the bottommost level of abstraction always in computing is zeros and ones. It's of it, right? If you go one higher, then it's actually right. You can call respect to decimal value. So that's also still not that clear. But this is decimal. This is hexadecimal. By the way, this one should be like this. These are not three numbers, guys. It's a single number in two rows. All right. So the next one. So now we start to realize what that is. So fractal list is represented by this page. So this ASCII or Unicode, right? So remember, one fact, another fact. Um, Unicode is a superset for ASCII as well. Right? So that means this is both in ASCII and Unicode. The letter is represented. Right? All right. So it's kind of backward compatible. Okay. All right. So then I and then exclamation mark and then the color purple and then they together gives us the purple color high, right? So that we understand, right? So that's the highest level of abstraction. So and you can see that to see just this one, you need this much of information behind the scenes inside the computer. And it's a lot of information to process for a human. So we actually practice abstraction to reduce that and to have better understanding. So that's basically abstraction in data. So if you go to real world, right? So here's a good example, right? Let's say this desk, right? Right? So we have the name desk or table, right? So when I say a desk or table, you guys can picture what it is, right? So I don't have to say, so referring to the desk, I don't have to say the thing with four legs and one top, right? I don't have to say that, right? I say desk, and you understand what it is. So basically, by you know, like by categorizing all those of information that goes into single entity and giving it a name so that we can recognize it, it's an abstraction. So we actually practice in the real world. Right? So every language has it. So the reason why we do that humans because that way we can process. We don't have to process that many of information. We basically bundle it to a single entity and give it a name. Right? And we can do it for verbs. So we have some actions. We have verbs for that, right? And for things we have names, right? So that's actually abstraction in reality. So we can basically take the same into computer science as well. All right. Any questions? All right. So we can actually talk about so that I think we can now move on to our so let's actually do this. Um, yeah, we are actually almost done with this section. All right. So we can actually do the activity today. So this supposed somehow when I publish it, actually all of them were published. So okay, some of you guys only did this stuff, but it was supposed to be published today. But that's fine. Okay, so we can actually do this one right now. So if you already submit this one, guys, go to the file book and then you can print it out. Otherwise, we're gonna do it together in pairs. Remember the partners. So find the partner that you performed the other day, right? So if that partner is missing, you can find a different one. So let's do it together. Okay. This is what we are going to do. Okay. All right. So, so let's wait a little bit, and I'm going to show you what you guys need to do. Okay. So doing all of this, we are actually making a good solid foundation to start learning how to code starting with code. Okay. All right. So okay. So let's take this example. Example in there, take writing an email, right? So, right. So let's take that. So that's a verb, right? Right. So um, when it comes to writing an email, what are the inputs? Subject, right? So let's write the input. Subject, subject. What else do we need? Yeah, so the emails we are going to send in, right? So the emails. Three, do we have three? Anything else? That's emails, yeah. That's okay. You're right. Yeah, those things also there, but the most importantly, what we need. Yeah, the thing that we want to communicate, right? So the text, right? So what we need to write, right? So that's the input, right? So what's the outcome? The output. Yeah, the finished email or sent email, right? That's the output, right? So the email finished, right? So in between we have the process, right? So that's actually write email, right? Notice that it's a verb, right? Because it's actually this one, we are talking about an action here, right? So, but the action is writing an email. So, and then this is basically the abstraction, right? So when we say we write an email, so we don't need, we know what it is, right? So we don't need to describe every single nitty bitty thing that we do writing emails in here, right? We simply say write email, right? So, so that's the black box, right? So this is the black box, right? So we basically it has a name and we know what it does. We don't need to know how it does because how it does is too much of information to process or fathom, right? So we give it a name. By name, we know what it is. So basically, relying on what the outcome rather than how the output or outcome generates is actually a form of abstraction, right? And it's required because having to process every tiny detail of information is too much of a burden for our brain. That's why we practice abstraction. Okay. So what you need to do is then pick a verb, figure out the input. So no programming yet, right? So, but we're gonna easily transform this to programming as well, starting with code. So, figure out an action in English, in reality, real world. Figure out the inputs. Write it like this. Could be one input, could be many that as well. So we call this the black box, and there should be a name for it. That's the name of the action. So, write email, something like that, or drive a car, something like that. And the output should be this. Then you could have two arrows like this. That's it. That's your assignment today. So this should be quick, right? So pick a verb and then figure out those things. Then you can draw it in a paper and then take a picture and submit, or you can do it. You can use technology if you have. You can use the touchpad or anything as well. So how do you submit if it's an image based? So click on reply. Some of you already have submitted because it's not published actually. If it's an image you taken from your cell phone, insert, image, upload. That's the workflow. Okay? All right. That's it. Yes.